Hi everyone, we're starting section 16E on compound interest versus simple interest. So we're going to go right straight into examples and explanations. Alright, so if we had $1,000 and the bank was paying an interest of 10% on that $1,000, alright, so and it was annual, so we're looking at annual interest rate, and I would take $1,000 at the end of year one. I would have $1,100 because 10% of 1,000 is 100. So on top of the $1,000 that we have, you would add $100 to it every year. So this is what we're looking at. We're looking at adding $100 every year, and it's based on the original amount that we started off with. So that we're looking at the original amount. So I'm taking 10% from the original amount, so that we have $100 being added on every year. Now, a situation like this would look like a linear equation, because what we're saying is that for every year that goes by, $100 is being added every time. So we have a constant, or we've got a slope of a constant slope where we are increasing every year by 100. So I go ahead 1 year, so I go from 0 to 1 year, it's $100 more. I go from year 1 to year 2, it's another $100, and so forth. So that turns out to be a linear graph where we're adding $100 per year. If we were to look at, though, and compare it to compound interest means that we are taking the $1,000 original amount that we have, and by the end of year 0, getting into year 1, we would have $1,100. Now, instead of adding on $100 every year, what that's doing is, in compound interest, is that you are taking the previous year's amount and multiplying it by 10%. So I'm multiplying, or I'm adding on a 10% from the previous year. So we went from $1,000 to $1,100, and then we take 10% of 1,100 to give us 1,210. Then we take 1,210 in the following year and add on 10% to that, so that we get 1,331, and so forth. So that you are doing a multiplication in this case. So every next year is going to be a result of the previous year's amount multiplied by 10%. So it's an adding on. You're always adding on a little more. And as you can see, you're making a little bit more. If we compare the two types of interest rate, or type of interest, then we've got 1,000 starting for both of them, and at the end of year 1, yes, we have $1,100 in both. But by the end of year 2, we see that in simple interest we will have gained only $1,200, and we will have gained by the end of year 2 $1,210. Now, that amount of money seems very little, and you say, okay, it's only $10 more, but as you go further up in the exponential growth of the compound interest, what you'll see is that the amount of money that's being earned is getting higher as the number of years increase. Because as we know, however, we know that exponential graphs start off quite slowly, and they seem to rise at a faster rate after we get past a certain number of years, or whatever it is that we're looking for. In this case, we're talking about number of years. All right, so that compounding is going to be exponential, and we know that simple interest, when we're looking at it graphically, is nothing more than a linear graph where you are adding on a constant amount every year. All right. So when we look at the next page, we're going to just take a quick look at the simple interest formula and the compound interest formula, because there's two different formulas for this. So when we look at simple interest, we say that the interest is going to equal the amount borrowed, or the amount of money that you start off with. So it's the principal or the present amount of money that you have, whatever you want to call it, the principal value, the amount borrowed, and then R is going to be your interest rate, and T is going to be your time. So if we take a look at the actual formula, the amount of interest that you're going to be paying is really going to equal the amount of money that you borrowed multiplied by the interest rate that you borrowed the money for, and then the amount of time you're going to take to pay back that money. So if we had an example like Ian borrowed $3,000 for 4 years at a 5% interest rate, the question is, how much interest is that going to be that you're going to be paying on top of the principal or the amount of money that you borrowed? So we'll use I equals PRT, and I is what we're looking for. We want to know how much interest is he going to be paying, okay? So that we can say that $3,000 is our principal, or the amount of money that we started off with, and our rate, now this is what you need to keep in mind, is that the interest rate is 5%. But 5%, when we write that as a fraction, will go to 5 over 100. And 5 over 100 is nothing more than 0.05. So we rewrite it as a decimal so that we get 5% being equal to 0.05. And that gets multiplied by the number of years that you're going to be borrowing the money for, which is 4 years. And when I multiply all that out, I get the interest is equal to 600. So what that is simply saying is that on top of the $3,000 that you're going to have to pay back at the end of 4 years, there will be an extra 600 just for having borrowed the money. That would be your interest for having borrowed that amount of money of $3,000. Now, if we look at the compound interest formula, the compound interest formula says that their future value, so I mean this makes very much sense, the amount of money that I'm going to have in the future is going to equal the present amount of money that I have now, or the original or initial value of money that I have now, okay, times 1 plus I is the interest rate, written as a decimal, and that's raised to the power of the number of years that you are going to be doing this investment for. So, when we have to write out the part inside the parentheses here that says 1 plus I, that 1 plus I stands for, because we're looking at exponential growth, and we're saying we're taking our previous value and multiplying it by the interest rate, well, what we're actually saying at this point is that I have my 100% that I start off with. The amount was my 100%. And that interest that I pay is going to be, or that I pay or that is being paid, is going to be on top of the 100% that's already there. So that if we look at the first example, it says, if the present value of my investment is $1,000 and the rate of interest is 6%, so my rate of interest is 6% and it's compounded annually, what will be the value after 10 years? All right. So we know that the future value is going to be equal to the present value, 1,000, times 1 plus the value of I. Remember that I is our interest, and our interest rate is 6%, which I'm going to divide by 100, and it'll go to 0.06. So that my exponential growth is going to have to be 1 plus 0.06. because it's 6% on top of what we already have, 100%. So that this will go to 1.06. And it makes sense, because in order for this to be exponential growth, really it would have to be, the value of A in this case would have to be bigger than 1, and 1.06 would be greater than 1. So when I now do 1,000 times 1 plus 0.06, and that's all raised to the power of 10, my order of operations tells me to do 1 plus 0.06, raise that to the power of 10 first, and then multiply it by 1,000. And we get 1,790.85. So the amount of money that I would be getting on top of the $1,000 that I had originally, I'd be getting approximately $790.85. Okay, so let's take a look at another example. So it says that your goal is to have $3,500 in 10 years. And the rate of interest is 3%, which is being compounded annually. So the question is asking, how much should we start out with? So we know what our future value is. We know that our future value is equal to 3,500. And we're trying to find our previous value, and we know that our rate of interest is 1 plus, and now I take the interest rate of 3%. I turn it to 3 divided by 100, which is equal to 0.03. So inside the brackets, I will have 0.03, and that will be raised all to the power of 10. So all I need to do is say 3,500 is equal to P sub V of 1.03 raised to the power of 10. I divide both sides by 1.03 raised to the power of 10. And I end up getting that my previous value should have been, working it out very quickly, my value should have been then 2,604.328 approximately, or we can just cut it down to $2,604. So that was what my original value would be in order for me to reach $3,500 in 10 years. We're looking at approximately $900. Not very much, but that's pretty realistic. Actually, it would normally be even more. Interest rates usually aren't as high as 3%. All right. So let's look at a couple of other examples. So we've got an example here that says you have $1,000 and you want it to grow to $2,000 in 4 years' time. And the question is asking, what compound interest rate do I need to have? So again, using the compounding, we've got that the future value is going to equal the previous value times 1 plus the interest rate raised to the power of n, which is your time. So I know that presently I've got $1,000, and I need to find out what the value of I is when it's raised to the power of 4. That's my time. And I know that my future value needs to be $2,000. So what I do now is I need to isolate for the value of I, or the interest rate, the compound interest rate. So I will do 2,000 divided by 1,000 is equal to 1 plus I raised to the power of 4. And this will go to 2 is equal to 1 plus I raised to the power of 4. And now I need to get that I out of the power of 4 here. So what I can do is I can multiply both sides of the equation by 1/4. So by multiplying by 1/4, I get rid of the 4 and the 1/4. So I get 2 raised to the power of 1/4 equals 1 plus I. And when I calculate 2 raised to the power of 1/4, I end up getting that my answer is 1.189 is equal to 1 plus I. So when I subtract the 1 and I bring it to the other side, 1.189 minus 1 equals I get that I is equal to 0.189. And 0.189, when it gets multiplied by 100%, it will give me that the percentage is 18.9%. And it'll be, which is approximately 19%. So we know that it's 18.9% in the answer to this problem. All right. The next section that we can look at very quickly is the section on section F, which is depreciation. So depreciation means that I am not looking at exponential growth, but I'm looking at exponential decay. When something is losing its value, it's called depreciation. So for example, a car, as soon as it comes off the lot, it depreciates or it loses its value. And I could say that maybe it loses its value 15% per year, let's say. All right, so I could say that my future value is equal to my present value, the original purchase price, or how much, or the present value. And instead of having 1 plus the amount of interest, or the amount that it would depreciate, instead of having 1 plus, we're going to have 1 minus the interest. Because that's the amount, that's the percentage that something is decreasing in value. So instead of adding on, we're subtracting. And again, it makes sense, because when we think about it, if I'm looking at depreciation, it means that something is losing its value. And if it's losing its value, it's not possible for it to be exponential growth, but it must be exponential decay. And if we're looking at exponential decay, that means that our value of the base of the exponential has to be between 0 and 1. And if I do 1 plus the interest rate, that would give me a value greater than 1, which would be exponential growth. So in order to get exponential decay, it would have to be 1 minus the interest rate. So it's exactly the same formula as we saw in section 16E for compound interest. The only difference is that when we are depreciating something, that means we're going to do 1 minus the interest rate and not 1 plus. But the formula is essentially the same. So if we look at the example that's underneath here, we have that the value of Lynn's car depreciates at about 15% per year. If she purchased her car for $21,900, what would its value be in 10 years? So I'm going to do the future value equals the original value times 1 minus 0.15, so it was 15%. Remember, 15 divided by 100 gives me 0.15. So I will now do 1 minus 0.15 raised to the power of 10. And it tells us that in 10 years' time, her car, which was $21,900, is going to be worth only $4,311.50. All right, so that pretty much covers everything that we need to do in this section. And you should be completing exercise 16E on the exponential growth, the compounding. So we're looking at the exponential, not depreciation, but the increase. All right, see you next time.